Hi, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 7. In this lecture, we'll discuss free fall. This topic is covered in Chapter 2 of our textbook by Surway and Jowett. In past lectures, we learned about the kinematic equations. The kinematic equations are the set of four equations that you see listed over here. These four equations relate the three basic kinematic variables: position, velocity, and acceleration. We've already seen how those three variables can be related to each other by differentiation or integration, but the kinematic equations essentially give us a shortcut for relating these three parameters. Integration can be time-consuming and is a process that is prone to mistakes. So for this simple but common case of constant acceleration, we prefer using the kinematic equations to find the velocity or position or acceleration or the time of an event for the motion of an object. Using the kinematic equations requires some practice. You need to recognize that there are 6 variables in total that are involved in this 4 set of equations. Of these 6 variables, 2 of them we can describe as non-critical variables. Those are x initial and v initial. We refer to these as non-critical variables because usually they are given in the context of a problem, or you can solve or decide what they are pretty easily at the beginning of a problem without many calculations. For example, x initial is usually set to 0. We often just assume that that's the starting position of an object. That's how we usually choose our coordinate system. V initial is usually given to you. For example, if you're told that a motorcycle starts at rest at a traffic light and then accelerates forward, that's basically telling you that V initial is 0. So these 2 parameters or variables are easy to figure out. But there are 4 variables that show up in the kinematic equations that are critical. These are a little more tricky to work with. These actually require, in most cases, a little bit of algebra or mathematics to solve. These are the final position, the final velocity, the acceleration, and the time for a particular event. So we have 4 critical variables and essentially 4 kinematic equations, and you have to be somewhat strategic or judicious in choosing the right equation for the right variable. And this, of course, all depends on the context of the problem and the information that's given to you. Usually when solving kinematic equations or kinematic problems, it's a good idea to make a list of the knowns and the unknowns. And looking at your list, you can usually decide whether you should be using equation 1 or equation 2, 3, or 4, or some combination of these 4 equations. As you look at these 4 equations, note that equation 1 does not depend on x final. X final, the final position, was one of the critical variables. So if a question is asking for the final position of a motorcycle, for example, then you should probably not be using equation 1. Equation 2 does not depend on v final, so that's not a good equation to use if a question is asking for the final velocity of a falling apple, for example. Equation 3 does not depend on time, so if you're asked how long does it take or how many seconds does it take for the race car to cross the finish line, you probably should not be using equation 3 because time does not show up in equation 3, so you can't solve for t. And equation 4 does not depend on the acceleration. If you're asked to solve for the acceleration, equation 4 is a bad choice. On the other hand, if you're not interested in acceleration and you don't know what the acceleration is, then equation 4 is a great choice because it doesn't show up anywhere in that equation. So this takes a little bit of practice to develop this sense of what's the right equation and what's the wrong equation, but hopefully as you're working through your homework, you're developing this sense. The kinematic equations can be used to analyze one-dimensional motion with constant acceleration. It doesn't matter if the one-dimensional motion is in the x direction or the y direction. In other words, it doesn't matter whether the object is moving horizontally or vertically. You can use the kinematic equations for either of those cases. We sometimes change variables from x to y if we're talking about vertical motion, but the basic mathematical structure of the equations remains the same. An important application of the kinematic equations is to free fall motion. And for the next few slides, we'd like to discuss how the kinematic equations can be used to analyze the motion of an object in free fall. When I speak of free fall, I'm referring to the motion of an object that is influenced only by the force of gravity. So free fall refers to basically an object that is falling, but the only force that is acting on it is the force of gravity. There cannot be any air resistance or propulsion or any other force that is acting on the object. On planet Earth, when most objects fall, technically they are not in free fall. For example, the skydiver jumping out of an airplane is experiencing some amount of air resistance, so technically the skydiver is not in free fall. However, it turns out when objects move relatively slowly, the effect of air resistance is negligible. We'll talk about air resistance at length in chapter 6, but for now you simply need to know that when objects are not moving too fast, we can ignore the effects of air resistance. So most objects that are falling under the force of gravity with not too much speed can be considered to be in free fall. Perhaps the most important characteristic of free fall is the acceleration of an object in free fall. Galileo is famous for having gone to the top of the Leaning Tower of Pisa and having dropped various objects of sizes and masses, and having noticed that they all fall with the same acceleration. That acceleration is 9.8 meters per second squared, at least on planet Earth. So near the Earth's surface, an object in free fall always experiences the same constant acceleration, regardless of its mass or shape or size. Now, technically, this is not exactly true. As I said, air resistance often plays a part. But if you were to drop objects in vacuum, for example, on the moon, where there is no atmosphere, then you would find that they do fall with a constant acceleration, and that acceleration is independent of the mass. At this point, it is not at all obvious why this acceleration is constant and why it is independent of the mass. To understand that fact, we will have to study Newton's law of gravity later in the semester. For now, what is important to remember is that when you are told an object is in free fall, you need to remember that it falls with a constant acceleration of 9.8 meters per second. And because that acceleration is constant, we can use the kinematic equations to analyze its motion. We can use the kinematic equation to answer questions like how long does it take for the ball to hit the ground, or how fast will it be going when it hits the ground, and things of that nature. As I just mentioned, the kinematic equations can be used to analyze the motion of an object in free fall. The only modification that we need to make is to recognize that acceleration, which shows up in at least 3 of the 4 equations here, is now 9.8 meters per second. So as you are solving for various parameters in a free fall problem, you need to remember that the accelerations that you see here and here and here now need to be replaced by this value here. This is for planet Earth. If you were analyzing the motion of an object in free fall on the moon or Mars, you would have to use the acceleration appropriate for that planet. Eventually, we'll talk about how you calculate this number for other planets. But for now, we'll keep everything on planet Earth, where the acceleration is 9.8 meters per second squared. This number is so common and seen so frequently that we often denote it using the letter G. So going forward, when you see the letter G in an equation, you just need to remember that it stands for acceleration due to gravity in free fall. And usually we're talking about planet Earth, so you can replace G with 9.8 meters per second squared. There is a subtlety here that we need to discuss, and that is the subtlety of whether this number should be plus 9.8 or minus 9.8. The answer to that question depends on the coordinate system that you're using. Whenever you're using the kinematic equations, if you want to talk about position, velocity, and acceleration, you need to have a coordinate system in mind, and it's the choice of coordinate system that determines whether the acceleration should be plus 9.8 or minus 9.8. We'll discuss that fact in more detail on the next slide. Here's a practice problem involving free fall motion and the kinematic equations. The Eiffel Tower is 324 meters tall. Standing at the very top, you throw a baseball straight down with an initial speed of 5 meters per second. How long will it take for the ball to hit the ground? So obviously this is not something you want to do in real life. Throwing anything down from the top of the Eiffel Tower is a bad idea, but for the sake of physics, let's pretend that this is exactly what you did. So you're 324 meters off the ground, you're looking down and you throw, you don't just drop, but throw a baseball straight down with an initial speed of 5 meters per second. We want to know how long it will take for the ball to hit the ground. In other words, we want to use one of the kinematic equations to solve for t. Now, before we actually write down the kinematic equations, we need to set up a coordinate system. Without a coordinate system, we will not know what numbers to plug into the kinematic equations. There are several choices that you could make, and each one of you will have your own preferred coordinate system. Some of you might be thinking of this type of a coordinate system. Some people probably think, well, the origin should be placed on the ground, and up should be the positive direction. And if we're using this kind of a coordinate system, then the starting point of the baseball, x initial, is going to be plus 324 meters. The baseball starts at the top, that's 324 meters in the positive direction from where the origin is. So x initial is going to be 324. So in just a minute, when we start plugging numbers into our kinematic equations, for x initial, we're going to put 324. X final is the final location of the baseball. Presumably the baseball hits the ground. That's where we have placed our origin, the 0 of our coordinate system. So in this coordinate system, x final is going to be 0. The baseball is thrown downwards. Down is the negative direction. You can see according to this coordinate system, the arrow indicates the positive direction. So anything that points up or goes upwards is considered positive. Since the baseball is thrown downwards, we're going to say that its initial speed is minus 5 meters per second. Acceleration, or the pull of gravity, is pulling the baseball downwards. Because the baseball is accelerating downwards, we're going to say that the acceleration is minus 9.8 meters per second squared. The baseball is being pulled down. This coordinate system chooses up as the positive direction, so anything that points down is going to be minus 9.8. So in just a minute, when we start plugging numbers into the kinematics equation, wherever we see a in those equations, we're going to substitute minus 9.8 into that equation. Now we'll get to the kinematics in just a minute, but some of you might be thinking, well, why don't we put the coordinate system at the top of the Eiffel Tower? After all, that's where the problem begins. That's where the baseball starts its motion. So maybe that should be the 0 of our coordinate system. In this coordinate system, we're putting the origin at the very top, and we're again choosing the up direction as the positive direction. For those of you who want to use this coordinate system, x initial is going to be 0, because that's where the baseball starts. The baseball is going to end on the ground, which is 324 meters below the origin, so that's going to be minus 324. And just as before, because the baseball is thrown down and up is the positive direction, we're going to say that the initial velocity is minus 5 meters per second and the acceleration is minus 9.8 meters per second squared. You might be thinking both of these choices are bad choices because the baseball is actually moving downwards. If everything is happening in the downward direction, why don't we choose this kind of a coordinate system? Let's put the origin at the top where the baseball begins, and let's just say down is the positive direction. This is a choice that you are allowed to make. The choice of what's positive and what's negative, in some sense, is an arbitrary choice. You, as the solver of this problem, have to make that choice, And you are free to say that down is the positive direction. If this is the coordinate system you're using, then x initial is going to be 0, makes sense. X final is going to be 324 meters away, and it will be 324 meters in the positive direction. So we're going to say x final is now positive 324. The baseball is thrown downwards, but we're calling down the positive direction, and so v initial is going to be 5 meters per second. And when we substitute acceleration into our equations, we're going to plug in plus 9.8 rather than minus 9.8. So notice how your choice of coordinate system affects the numbers that you will plug into your equations. On the next slide, we'll actually write down the equations and we'll plug in the numbers, and we'll see that no matter which one of these coordinate systems you use, you will get the same final answer, but the intermediate steps are going to be a little bit different. So here we're now using the kinematics equations. We're now going to plug in those numbers that we found on the previous slide. The kinematic equation that we want to use is this one. X final is equal to 1/2 at squared plus v initial times t plus x initial. Why are we using this equation as opposed to the other three? Well, because this has time in it, which is the thing I want to solve for, and I've carefully checked and noticed that I can figure out all of these other parameters that show up in this equation. If I want to use this equation and I want to use this red coordinate system, then the numbers that I plug in have to be this set of numbers. X final is 0. The acceleration is minus 9.8, so 1/2 times minus 9.8 gives me minus 4.9 t squared. The initial velocity, v initial, is minus 5, so I'm going to plug that in here. And x initial, we decided was 324, so that's plus 324. Look at this equation for a second. Hopefully you recognize it as a quadratic equation. To solve an equation like this, you need the quadratic formula. I trust that you know the quadratic formula, and I trust that within about 30 seconds, you can plug numbers into the quadratic formula and find that the solution to this equation is 7.637 seconds. That's how long it takes for the baseball to reach the ground. Some of you might not like the red coordinate system. You might like the green coordinate system. Well, not a problem. You would start with the same equation, the same kinematic equations. You would just plug in a slightly different set of numbers. X final is now minus 324. X initial is now 0. This is, again, another quadratic equation. In fact, if you're thinking about this critically, you'll notice that this green equation here is the same as the red equation here, because you can bring the 324 to the other side, turn this into a quadratic equation, use the quadratic formula, and again, you'll see that the time it takes for the baseball to hit the ground is 7.637 seconds. You might be using the blue coordinate system. You start with exactly the same equation, but the numbers that you plug in are going to be a little bit different. Notice here we have plus 4.9 and plus 5 for acceleration and the speed. But as you rearrange this equation and write it in the standard form and you plug numbers into the quadratic formula, you'll find once again that the time is 7.637 seconds. So you have to choose a coordinate system so you know what numbers to plug in, but at the end of the problem, of course, you'll get the same answer. And it should be obvious that you get the same answer, because if you look at the three equations that we solved, those three equations are really the same equation, just written in slightly different forms. So for example, if you take this second equation, the green equation, and you multiply both sides by -1, you'll get the blue equation, right? Or if you take the red equation and move the 324 to the left side, you'll get the green equation. So these three equations are really the same equation, just in different disguises, and so naturally they have the same answer. However, to get to the answer, you had to make a choice of a coordinate system so that you could have actual numbers to plug into these equations. To finish this lecture, let's do one more practice problem. This practice problem will have multiple parts, and each part will get progressively more difficult. This practice problem isn't really about free fall, but it is about the use of kinematic equations, which are the main topic in chapter 2. Starting from rest, a police motorcycle is capable of achieving a constant acceleration of 6 meters per second squared until it reaches its maximum speed of 55 meters per second. At what time and what distance does the motorcycle reach its maximum speed? So you can imagine riding this motorcycle. You start at rest, you rev up the engine all the way, and you achieve your maximum acceleration. For this motorcycle, the maximum acceleration is 6 meters per second squared. As you achieve this acceleration, the motorcycle goes faster and faster and faster. After 1 second, it'll be going at 6 meters per second, then 12 meters per second, then 18 meters per second. Every second that goes by, the speed increases by 6 meters per second, until the motorcycle reaches its maximum speed of 55 meters per second. After that, it cannot go any faster. So the needle on the speedometer has maxed out, and that's the top speed for this motorcycle. And the question is, when does the motorcycle achieve that maximum speed? Well, I need the time and also the x-coordinate, or the position where that happens. To find the time, we will use the kinematic equations. At this point, you should have the kinematic equations maybe in front of you. You should be going through them one by one, checking some of them off, xing some of them out, depending on what parameters are given to you. Eventually, you should discover that this is the right equation of the 4 to answer this particular question. I like this equation here because it has time in it, so I can solve for t, and I also know what the initial and the final velocity are, and the acceleration is given to me. So this is a nice equation because all the parameters are known except the one that I want to solve for. V final is 55, the acceleration is 6, V initial is 0 because the police motorcycle starts at rest. And so the equation that we have is 55 is equal to 6t. If you solve for t, you will see that it takes the motorcycle 9.167 seconds to achieve its maximum speed. So that answers part of the question, at what time does the motorcycle reach its maximum speed? But what is its x-coordinate? What is its position? Or what is the distance that we'll have traveled in those 9 seconds? Again, we're going to go through our kinematic equations, and we're going to find that this equation here is a nice one. If you look at this equation here, you'll see that everything is given to you. X initial is 0, V initial is 0, the acceleration is 6, and the time, well, we just figured out the time. It's 9.167 seconds. Don't forget to square it. So you can plug all that in and get the final position of the motorcycle. That's when the motorcycle has achieved the speed of 55 meters per second. If you plug all those numbers in, you'll see that the x-coordinate of the motorcycle at that moment in time, when it has maxed out its speed, is approximately 252 meters. If you have the kinematic equations next to you and are thinking about them critically, you should probably recognize that you had another option. Among your 4 kinematic equations, there is another one, this one listed here, that would have also allowed you to solve this second part of the problem. If you look at this equation here, you'll notice you know what V initial is, you know what V final is, you know what acceleration is, you know what X initial is. So you could have used this equation as well to solve for X final. In fact, you can now plug in 55 for V final, 0 for V initial, the acceleration is 6, X initial is 0, and now you can solve this equation for X final, and if you do that, you'll see that you get, again, 252 meters. So it's exactly the same answer as we got before. This is a nice check on our calculations. If you're solving this problem on a test, I recommend checking your answers in this manner. Notice that our first method using this equation actually used the time, but the second method did not use the time. So on an exam question, if you're not sure about your calculation of time, this second method might be superior. Here's part B of the same problem. So we have the same police motorcycle. It can achieve a constant acceleration of 6 meters per second squared until it reaches its maximum speed of 55. Tell me, what is the motorcycle's position at 15 seconds? Now, this is a slightly more challenging problem than part A, because you should be thinking that things are changing in the middle of this problem. This police motorcycle has an acceleration of 6 meters per second squared, but it doesn't have that acceleration up until 15 seconds. It has an acceleration of 6 up until about 9 seconds. That's when it maxes out, right? We found that on the previous slide. After 9 seconds, the police motorcycle travels at a constant speed. When something travels at a constant speed, its acceleration is going to be 0. In fact, if you were to make a graph of the acceleration of this motorcycle as a function of time, you would find that it looks something like this. The acceleration at the beginning begins at 6 meters per second, so this is 6 meters per second squared. But then right around 9 seconds, approximately, the acceleration basically drops down to 0. Why does it drop down to 0? Well, because the speed has maxed out. This motorcycle, the engine, is simply not capable of providing any more power for acceleration after the motorcycle has reached a speed of 55 meters per second. What this tells us is that this part of the problem is really a two-stage problem. We need to look at what's happening in the first 9 seconds of the problem, and then we need to look at what's happening in the next 6 seconds of the problem, all the way up until time 15. This is a two-stage problem because the acceleration is changing. Remember that the kinematic equations are designed to handle problems where the acceleration is constant. Here, the acceleration is constant for 9 seconds, but for the subsequent 6 seconds, it's a different constant. So I need to treat this as a two-stage problem. For stage 1, I'm going to say the acceleration is 0. I'm going to choose this particular kinematic equation here. I know the acceleration is 6. I know that stage 1 goes until 9 seconds, or 9.167 seconds. This is the answer we found in part A. Don't forget to square it. X initial is 0, V initial is 0 because the motorcycle is starting at rest. And when you plug all that in, you get 252. This should not be a surprise. We've basically already done this calculation in part A of the problem. So here I'm simply saying that in stage 1 of the motorcycle's motion, it will travel 252 meters. What's happening in stage 2 from 9 seconds to 15 seconds? Well, during that second stage, the acceleration is now 0 meters per second squared. I'm going to use the same kinematic equations, but the numbers that I'm going to plug in are going to be a little bit different. For acceleration, I'm now going to plug in 0. The time is now 15 minus 9.167, so these 9 seconds correspond to stage 1. The amount of time that we spend in stage 2 is basically the difference between 15 and 9. You square that. V initial is 55 now. Remember, this is stage 2. The motorcycle has already maxed its speed. It's just cruising at a constant 55 meters per second for the whole time. So that's V initial. For the time, again, I'm not going to plug in 15. I'm going to plug in 15 minus 9 seconds. So I've already accounted for the first 9 seconds. Here I'm trying to account for the next 6 seconds. And then X initial is going to be 252. The 252 is the final X coordinate of stage 1. So that's this number here. Notice how X final for stage 1 becomes X initial for stage 2. So I'm sort of building these stages on top of each other. Stage 2 is kind of picking up where stage 1 left off, right? The final position for stage 1 becomes the initial for stage 2, and now I can plug all this into my calculator, and I'll find that X final at 15 seconds at the end of stage 2 will be 572 meters approximately. So after 15 seconds, this is how far the police motorcycle will have traveled. Here's part C of the same problem. The police motorcycle is waiting at a speed trap. A speeding car drives by at a constant speed of 40 meters per second. The police motorcycle begins pursuit, accelerating at 6 meters per second squared as before. How long will it be before the motorcycle catches up with the car? I would say this is a rather challenging problem. This is probably the most difficult part of this problem. But I think if you want to get an A in this class, this is the type of problem that you should be able to solve. So it's the same motorcycle, it has the same acceleration and the same top speed, but this time it's chasing a speeder. The speeder does not have any acceleration. You could say the acceleration of the speeder is 0 because it's moving at a constant speed, and its constant speed is 40 meters per second. So initially the speeder is traveling significantly faster than the police motorcycle, but the motorcycle is going to accelerate and it's going to hope to catch up with the speeder. The question is, when will it catch up? Now notice that the position of the police after 9 seconds is going to be 252 meters approximately. I know this because this is a calculation we've done twice now. We can figure out the final position of the police motorcycle after 9 seconds. Remember, 9 seconds was that crucial time when the police motorcycle reaches its maximum speed. And at the same time, we can figure out the position of the speeder after 9 seconds, and we will see that its position will be 366 meters approximately. Notice how I'm placing these subscripts on X now, because now I need to keep track of 2 different coordinates. I have 2 different objects. I have the police and I have the speeder, and each one is going to have its own velocity and its own position and its own acceleration. So we now need to be kind of very careful about how we label our coordinates. Here I'm labeling any variable that has to do with the police with a subscript P, and X sub S refers to the position of the speeder. Clearly, after 9 seconds, the police has not caught up with the speeder just yet. In fact, you can see that the speeder is significantly far ahead of the police after 9 seconds. Now, this is kind of important because this tells me whether this is a stage 1 problem or a stage 2 problem. In the previous part of this problem, in part B, we had to solve the problem in 2 stages because the acceleration of the motorcycle was changing from 6 to 0. Well, that's what's going to happen here as well. Clearly, this problem is not done after 9 seconds, so now we need to enter the second stage. What's the position of the police at time t in stage 2? Well, in stage 2, the acceleration is 0, so I'm going to leave that part out. Then I have velocity times time, but time is going to be t minus 9 seconds. Remember, we're subtracting the 9 seconds because now we're talking about stage 2 of the problem. We add the final position of stage 1 as the initial position of stage 2. So we're accounting for the stage 1 motion by adding 252 meters and subtracting 9 seconds from the time. Now this gives us the position of the police. What is the speeder doing? Well, I can use the same equation for the speeder, but the numbers are going to be a little bit different. The speeder is moving at a constant speed of 40 meters per second. I already know that the speeder will have traveled 366 meters in stage 1, so I'm going to add that to this coordinate here, but I'm also going to subtract 9 seconds from the time because I've already accounted for those 9 seconds of motion. Now this describes the situation for stage 2. I now have coordinates for the speeder and the police for stage 2 of the problem. How do I figure out when the police catches up with the speeder? Well, think about what it means to catch up with something. When you catch up with your friend, what that really means is that you're at the same place at the same time with your friend. Here in this particular problem, if we want to talk about the police motorcycle, quote unquote, catching up with the speeder, we're basically saying at what time do they have the same coordinate, right? So what we really want to do is set these two equations equal to each other. When the position of the police is equal to the position of the speeder, we can say that one has caught up with the other one. So set these two equations equal to each other and solve for t. I encourage you to do this algebra on your own. And as you're doing it, you should find that t is approximately equal to 16.8 seconds. So it takes about 16 seconds, maybe 17 seconds, for this police motorcycle to catch up with the speeder. Notice what made this problem kind of difficult is that it's a two-stage problem. There are multiple accelerations involved. The acceleration of the car, the speeder, is 0 the whole time. The acceleration of the police motorcycle is 6 initially, but then it's 0 finally. So after 9 seconds, the acceleration changes. That change in acceleration means that you need to solve this problem in stages. Here is part D of the same problem, and this is the final part of this very lengthy problem. We're essentially done with this problem, but to gain some additional insight, I want you to try and make graphs of acceleration, velocity, and position for the police motorcycle and also the speeder. And I want you to plot these things as functions of time. Graphing these things might be a little bit tedious, but by looking at the graphs, hopefully you can gain some additional insight into this problem. Here are graphs of acceleration versus time for the speeder in blue and the police in red. As you can see, the acceleration of the speeder is basically 0 the entire time, from 0 seconds well up until 20 seconds. For the police motorcycle in red, the situation is a little bit different. The police motorcycle initially revs up its engine and accelerates at 6 meters per second. So this is when the police motorcycle is speeding. But once the speedometer reaches its maximum speed, the police motorcycle cannot go any faster. That doesn't mean that he stops moving. He's going to continue to move at a pretty fast rate, but his acceleration is now going to drop to 0. So after about 9 seconds, both the speeder and the police are moving with an acceleration of 0. So they have the same acceleration, but they most certainly do not have the same speed. Here are graphs of velocity or speed versus time for the speeder in blue and the police in red. As you can see, the speeder is pretty simple. The speeder is traveling at a constant speed of 40 meters per second the whole time. He's not speeding up, he's not slowing down. The police motorcycle, on the other hand, is trying to catch up with the speeder. He starts at rest, he revs up the engine, he goes faster and faster and faster and faster until he reaches his maximum speed of 55. That happens around 9 seconds. And then from there on, the police motorcycle cruises at 55 meters per second. What about the position? Well, the position graphs are probably the most complicated. The position graph for the speeder is shown in blue. You can see it's a straight line. The position is initially 0 and then it gradually increases. The speeder is traveling at a constant speed, so the slope of the blue line is constant. Since the speeder is traveling at 40 meters per second, every second that goes by, his position increases by 40. So he's going 40 meters farther every second that passes. And that basically results in this linear graph, the blue graph that's increasing here. The police motorcycle has a more complicated situation. You can see initially the graph is somewhat curved. To be more precise, it's a parabolic graph. It's a parabola, right? And that's because initially, for the first 9 seconds, the police motorcycle has an acceleration of 6. After 9 seconds, its acceleration is 0. That doesn't mean it has stopped moving. It's still moving. It's moving really fast, 55 meters per second. It's just that it's not moving any faster. From there on, the graph for the police motorcycle also becomes a straight line with a greater slope. Remember that the slope of these lines basically tells you the speed of the object. And then you can see right around 16 seconds, those two graphs intersect. So right around 16 seconds, the answer we found on the previous slide, is when we can say the police motorcycle has caught up with the speeder. So the precise numbers are found by doing the algebra that we did on the previous slide, but by looking at the graphs, you might get a better feel for what's going on in this particular problem. And that's the end of this lecture. Thank you for your attention.